If we have a circular loop, it doesn't necessarily have to be a circular loop, but in this problem it will be. We have a circular loop of wire run by a source, and we have a switch here, so we can close the switch and get the current going, or we can get the current going and open the switch and see what happens. Or we could, of course, drive this thing with some kind of a variable source. This is a direct source, a constant source, but we could drive it with a variable source. And we assume we have some sort of resistance. This wire has resistance. Maybe we have a resistor in here somewhere. But in any case, we drive a current I in a loop of radius A. Now, when the current is I, the field at the center of the loop is, as we've developed elsewhere, and I did that off to the side here just to remind us, but we have B equals 2 pi K prime I over A times the K vector. Now, the K vector comes from what I did over here when I did this in 3 dimensions. And that would correspond to the loop being here in the XY plane, X in this direction, Y in this direction, Z coming out of the board. Okay, and I'm a little fuzzy today, so if I fail to get the right word and hesitate a little bit, don't be surprised. You've seen me do that repeatedly anyway. Okay, so we get our field, which has magnitude 2 pi K prime I over A, and that's the field at the center of the loop. Now, the argument for that I'm just going to briefly allude to, because I've done that in other videos and I've done it in more detail. But this is an argument you should be able to reconstruct for yourself anytime. It actually involves an integral, but you don't really need to do an integral to get the result because everything's constant. So we have a delta S on a loop, and we have the R vector to the center, and we're trying to find the magnetic field at the center of the loop. And we could draw the magnetic field that we get. If we do the I delta S cross R, we get a vector perpendicular in this direction. So we're going to get delta B, and it's going to be in the positive Z direction, so that our delta B, if we follow the rule, is going to be K prime times I delta S times the R vector over R squared. And we've done this in some detail, so we should understand this. When we simplify this, the delta S cross R divided by R gives us the K vector, as we just saw. So that, and of course it's going to be delta S times the K vector, or I delta S times the K vector, in any way you want to look at it. We get K prime I delta S times the K vector over A squared, assuming a loop of radius A. So R becomes A. The R vector is as you see it, etc. Okay, now when we sum those up, everything in this sum is going to be constant, except perhaps the delta S. So we can factor out the K prime I over A squared times the K vector and just sum up the delta S's. Now, and what that really means is it doesn't matter where this loop is or where this segment of the loop is, we're still going to do the R cross, the delta S cross R, and we're still going to get something parallel to the K vector. And the magnitude is going to be delta S times K, or I delta S times K if you wish. So we can sum up all the delta S's around here to get the sum of all the delta B contributions, and we end up with this and this, and that's the sum of the delta S's is just 2 pi times A. Okay, I've indicated that here, and that gives us our result. So that's where this comes from. Okay, well, if we assume, and this is not a valid assumption, it's not a particularly accurate assumption, so I'm going to stop and write a little disclaimer on here. Okay, I've written it's not so, but let's assume a constant magnetic field B over the entire enclosed area. And that gives us a reasonable order of magnitude approximation, as indicated in the problem as it was written. So we get what? Magnetic flux is going to be this constant magnetic field, the magnitude of the field, times the area of the circle. The magnetic field is perpendicular to the plane of the circle, so that the magnetic field dotted with the area vector, we're going to have a K dotted with a K, because the area vector is going to be equal to the area times a K vector. And we're just going to end up with this, and it's very straightforward. And we simplify it, we get 2 pi squared K prime I times A. Now, the question we want to answer then is, if I is varying, as it would be if we started this thing with an open switch and then closed the switch, I would have to vary. Or if we have it running and then suddenly open the switch, I would have to vary. Okay, we can't actually just open the switch here. We have to set up the circuits in a slightly different manner, but let's just take this as if we could. Okay, in any case, if for one reason or another I varies, this magnetic flux is going to vary. If the magnetic flux varies, then we're going to get an EMF out of that varying flux that's separate from the driving voltage. Okay, so the EMF, and I'm going to call this EMF induced. I'm going to write IND there for induced. The induced EMF is equal and opposite to the time derivative of the flux. Okay, so, well, what's that? Well, the flux is 2 pi squared K prime times A multiplied by the current. And the current's the only thing in here that can vary. All these other quantities are constant, so we have the constant quantities here multiplied by the derivative of the current. And again, that gives an induced current. So that more generally, the induced current, and I'm looking for a red piece of chalk here, and I don't see one. Here we go. The current induced in a loop or coil or a solenoid is proportional to di dt, where I use a lowercase I, as I should have here, to indicate a time-varying current. And see if I've got room to write this. The induced current, we're going to say, is equal to negative L times di dt. And hopefully that's legible down there. L is called the inductance, and E is again the induced EMF. And the induced EMF is going to be opposite. It's going to oppose the change in current, so that's why the negative. Okay, if the current is changing in a positive direction, if the current is increasing, then the induced EMF is going to tend to oppose that. So we have a negative induced EMF. If the current is decreasing, then the negative of this would be positive, and we would have a positive induced EMF. And this quantity L, if I didn't mention it, is called the inductance.